So in this lecture, we're going to look at a relationship between the equilibrium constant of a redox reaction found in an electrochemical cell and that electrochemical cell's cell voltage, or its electromotive force. Now before we look at the relationship, let's remember what equilibrium constant is. So suppose we have the following expression or reaction in which we have two reactants and two products. Now our A reactant is in the gas state, our B reactant is in the liquid state, our C product is in the aqueous state, and our D product is in the aqueous state. So let's write the equilibrium constant expression for this reaction, and let's assume that equilibrium has been reached. So our equilibrium constant under standard conditions is equal to the concentration of product C times the concentration of product D divided by the concentration of product A. Now remember, whenever we're writing our equilibrium constant expressions, only aqueous molecules and gas molecules count in our equilibrium expression. We don't include liquid molecules or solid molecules. And that's exactly why we don't include the B molecule, because it's in a liquid state. So we only get this expression. No B is included. Now notice that this K is simply a ratio between the product concentration and the reactant concentration. So we say that if our K is greater than 1, that means our reaction is favorable. If our K is less than 1, our reaction is unfavorable. In other words, if it's greater than 1, that means our equilibrium lies to the right, because these guys completely react to form our products. In other words, if K is much larger than 1, we have very little of our concentration of A and a lot of concentration of products, namely C and D. Likewise, if K is much less than 1, that means we have lots of this guy left over at equilibrium and very little of formation of our products. And that means equilibrium lies to the left, which also means we have very little of this guy and a lot of this guy. Now let's look at B. So we just learned that the change in Gibbs free energy is equal to a negative N, the number of moles of electrons, times Faraday's constant times the cell voltage. Now from before, we know that the change in Gibbs free energy can also be expressed as negative R times T, well R is the gas constant and T is temperature in Kelvin, times our natural log of our K, our equilibrium constant expression under standard conditions. Now what we can do is set these guys equal. Why? Well, because this and this are the same expressions because they both equal the same thing, namely change in Gibbs free energy. So let's set these guys equal. So we get negative NF times E equals negative RT natural log of K. So we can basically rearrange this guy and solve for our cell voltage. And what we get is the negatives cancel, and we bring the N and the F to this side, and we get our cell voltage equal to gas constant times temperature in Kelvin divided by moles of electrons times Faraday's constant times natural log of our equilibrium constant. So this expression basically relates our cell's voltage and the concentration of our reactants and products, or the ratio of the concentration. Now notice in this equation, we have R is our constant, and F is also constant. And if we assume constant temperature of, say, 25 degrees Celsius, we can simplify this expression into the following expression. So let's rewrite this expression. Cell voltage E is equal to a constant times a constant in our case, because T is 298 in Kelvin. Since we assume that temperature is constant and temperature is 25 degrees Celsius, that's our assumption. That means in Kelvin, 25 plus 273 is 298. So a constant times our temperature that's constant divided by another constant called Faraday's constant, we get something called 0.0257, a number, right? So this expression under these conditions gives us the following simplified expression. And this expression is nice because here we have three unknowns. This is our unknown, this is our unknown, and this is our unknown. So if we, for example, know our cell voltage and we know our number of moles, we can rearrange this equation and solve for K in the following way. Natural log of K is equal to N times cell voltage divided by 0.0257. And suppose now we know our K and we know our N. That means we can use our equilibrium constant and our N to find our cell voltage. So these two equations become very useful. And these two equations build a relationship between the concentration of reactants and products and the cell's voltage. Now notice one interesting thing. Whenever we take natural log of a number that's bigger than 1, this expression becomes positive. And that means if this expression is positive, then this is positive. And recall that if our cell voltage is positive, that means we have a product favorite reaction. It's spontaneous. And that makes sense because earlier we said if we have a K greater than 1, that means we have a favorable reaction. Our reaction favors this going this way. Likewise, if this K is less than 1, if it's say 0.9, then this guy, our natural log of a number that's less than 1 becomes negative. So our E becomes negative. And that means if E is negative, our reaction is not product favored. It's reactant favored. And that means it's not favorable. And just like our K is less than 1, means that our reaction is unfavorable. The following thing I want to talk to you about is the following. I want to show you how we can convert the formula we just found to something simpler. Now notice we're dealing with natural logs. That means if we were to convert this log to exponents, we would have to deal with bases of E. Now bases of E aren't very easy to calculate. You need a calculator to calculate bases of E. For example, you don't know what e to the 1, e to the 2, e to the 3, well maybe e to the 1 you do, but e to the 2, e to the 3, e to the 4, you don't really know what that is without using a calculator. But bases like base 10, that's easy to calculate, right? 10 to the 1, 10 to the 2, 10 to the 3, that's easy to calculate. You don't need a calculator. And therefore our goal is to convert this natural log into base 10 log. And the way we do it is we have to remember from algebra what the base conversion formula is for logs. In other words, this is a formula that basically tells us we can convert any log of any base of any inside to the base of 10. So the way we do it is log of base x of y is equal to log of base 10 of y divided by log of base 10 of x. Now in our case, we have a natural log of some y, and that's equivalent to saying log of base e of y equals, that means we have to divide log of base 10 of y divided by log of base 10 of e. So this is exactly what we follow in this process here, in this step. Natural log of k is equal to log of base e of k is equal to, same exact process, this guy over this guy, same thing that we did here, is equal to. Now this is something we know. We know what e is. E to the 1 is some number. So we basically plug this guy into the calculator and we find that it's 0.434. So now we have log of base 10 of k is equal to this whole guy. And this guy is over this guy, right? So what we do next is we bring this guy over to this side. And that's what we do in step E. And we get log of base 10 of k equals, this guy is brought over to here, and what we get is 0.434 divided by 0.0257 times n times e. Now we plug this guy into the calculator and we get 16.89 moles of electrons times moles of electrons times cell voltage. Now in textbooks you'll find this formula, but this guy and this guy are the same. Now the way you go from this formula to this formula is you simply take this number and you raise to the -1 power and you get this expression. They're the same exact expression.